the mic here. Well, thank you very much, Olivier, and I'd also like to thank the organizers for inviting me here today. Very honored to be the first in this series of lectures on climate. And I'm going to talk to you today, as you've probably gleaned, about hurricanes, and in particular their relationship to climate. Hurricane Sandy, which many of you experienced last fall, is a reminder of how disruptive these storms can be. And Sandy wasn't, in some sense, even a hurricane when it affected this region. You can imagine what it's like when it gets up to Cat 5 or so. So the program that I'm going to try to take you through today is to begin with just a broad overview of the subject of hurricanes. What are hurricanes? Make sure we're all on the same page. Talk a little bit about observations and the physics of hurricanes. And then get to the topic of how does climate affect hurricanes? What do we expect from climate change? How have hurricanes behaved in past climate states? These are all very interesting questions to us. And I'm going to introduce, although I won't spend very much time on this really interesting topic that doesn't often get asked or even thought about, which is what is the possible role of hurricanes in the climate system? When we talk about hurricanes and climate, generally speaking, we're talking about a one-way effect. If the climate changes, how does that change hurricanes? But in fact, there are some reasons to think that hurricanes have a feedback on the climate system, and I'll tell you a little bit about that. And we'll talk about what hurricanes might have been like in the past, and perhaps in a more interesting way, how they might be affected by global warming. At the end of the talk, I'll present some new results that have yet to be published on this subject. So let's begin at the beginning with a little bit of an overview. Now, you notice that I've switched gears here. I'm not talking about hurricanes anymore. I'm talking about tropical cyclones. I need to tell you a little bit about the distinction between those two. What is a hurricane? Well, if you look up in a glossary, this is what you'll find. It's a tropical cyclone with 1 minute average winds at 10 meters altitude in excess of 32 meters per second, occurring over the North Atlantic or Eastern North Pacific. So several important points that we have to make just to clear the air. The generic term for this phenomenon is tropical cyclone. That's the term that's used by atmospheric scientists all over the world. Hurricane is a strictly parochial name that's given to this phenomenon only when it occurs in our neck of the woods and only when it's sufficiently intense. The etymology of the word itself is kind of interesting. It comes to us from various tribes that inhabited the regions around the Caribbean, the Caribs, the Taínos, Mayans, and so forth. They all had a god of evil, Unraken, whose image appears here. And I think this is very interesting. This one was lifted off of a Cuban vase, an ancient Cuban vase. And the natives were terribly frightened of this phenomenon because it was so destructive. And Christopher Columbus heard this word on his very first voyage and became savvy about hurricanes without actually having experienced one until his final voyage to the New World, when he was very clever about how he dealt with it, thanks to the knowledge he picked up. But the word Unraken was picked up by the Colombian Spanish and brought back to the Old World, went through different permutations to arrive at hurricane. Now, there's something else is interesting about this, sort of a spooky mask, and instead of ears, these spiral arms, looking a little bit like the image that modern meteorologists put on weather maps to denote the presence of tropical cyclones. And I can assure you that the folks who came up with this didn't know about this guy, okay? The modern meteorologists use this to kind of denote rotation. We all know that hurricanes are rotating storms. Well, we in the West know that, have only known that, since about the middle of the 19th century. All right. Before that, it was not known. But there's an intriguing suggestion that the ancient inhabitants of the Caribbean region understood that. If you see the suggestion of rotation in these spiral arms, not only that, but it's the correct sense. We'll never know for sure, but maybe they somehow understood that these were rotating vortices way back then. Hurricanes, it's sort of a hobby of mine to understand how hurricanes have influenced history, and I could spend the entire hour telling you all kinds of stories, even without the benefit of slides, that I think you'd find entertaining about hurricanes, but I'll limit myself to one or two, how hurricanes have influenced history. One of the earliest incidents that we know about dates back to the 13th century, when twice Kublai Khan tried to invade Japan with very, very large armies, using boats that he had built by the newly conquered Koreans. The first time he tried was in 1274 with an army of only a few thousand, I think 10,000 men, but that's a staggering army for that day. When you consider, for example, the Norman conquest of England only took 3,000 soldiers. This was an amazing feat. But they had crossed the Sea of Japan and probably would have taken Japan had it not been for a tropical cyclone that blew up and basically destroyed his fleet, although Kublai Khan himself got away with his life. Not to be thwarted, he came back 7 years later in 1281 and tried again with a much larger army at that time, only to have history repeat itself and blown to smithereens by a hurricane. That is that set of incidences led to the origin of the famous Japanese word kamikaze, which translates more or less in English as divine wind, which is the title of my book, because understandably the Japanese considered these hurricanes to be their saviors. If it hadn't been for these storms, I mean, one can conjecture its virtual history that Japan might be part of China today. We'll never know. Now, closer to home, some of you may know that the worst natural disaster in the history of the United States, in terms of loss of life, was the Galveston hurricane of 1900. And I want to tell you a little bit about that by way of telling you historical stories. There were a lot of things leading up to this event. You know, when we talk about natural disasters, I think it's important to realize that it's kind of a marketing term. It's a term that we use to persuade ourselves that it isn't our fault, but of course it is. It's not a disaster for nature. Hurricanes are part of nature. It's a disaster for us because we insist upon putting a lot of flimsy material in risky places and watching it get blown away episodically. But in the case of this event, the hurricane that hit Galveston in 1900, a lot of interesting things leading up to it. The Galveston 1900 was the big port city of the Gulf of Mexico, the most important city in Texas. Of course, it isn't today, largely because of this event. And there was a very gifted and scientifically knowledgeable head of the local weather forecast office, Isaac Klein, who said this. You can see, you read it for yourself. The opinion held by some who are unacquainted with the actual conditions of things, that Galveston will at some time be seriously damaged by some such disturbance, he's referring to a hurricane, is simply an absurd delusion. Now, why would he say that? I mean, he knew there were hurricanes there. There was a famous theory by a very famous oceanographer by the name of Maury that was just plain wrong. It said that if you have waters that only become gradually shallow as you go offshore, that would prevent there being a large storm surge. A storm surge is physically equivalent to a tsunami. And you've seen these horrible movies of tsunamis recently, thanks to the terrible one in Japan recently. It's really the same phenomenon, but of course driven by wind, not by an earthquake. If you understand from looking at this film, that's what's happening, except it's happening in the middle of a violent storm. All right? Isaac Klein didn't think that could happen to Galveston, even though 4 years before this, a neighboring town, Indianola, was completely destroyed by a storm surge and a hurricane. So the residents of Galveston didn't think much of hurricanes. They weren't particularly worried about them because their forecaster wasn't. And this is what happened, okay? The hurricane came in. There were a lot of politics that prevented a warning that should have gone out in Galveston to do that. It's a very interesting and disturbing politics. Xenophobia on the part of the predecessor to the National Weather Service, didn't want any information coming into the United States from Cuba, and all kinds of horror stories. Anyway, the storm surge, the tsunami-like phenomenon, did this to Galveston. you look carefully, you can see two men, I think, standing over here somewhere examining the wreckage. It was a colossal problem, and it killed more than 8,000 people. And Isaac Klein said this, Sunday, September 9th, 1900, revealed one of the most horrible sights that ever a civilized people looked upon. So he learned very much the hard way. He lost his own family in the storm. That Maury, the oceanographer, was wrong about storm surges. Let's talk about what we know scientifically about hurricanes now, and I'll just begin with this nice satellite picture. You've seen pictures like this. This is a hurricane approaching the southeastern coast of the United States. There's Florida in the upper part, the Carolinas here. When you look down from space, you see a swirling mass of clouds a few hundred miles across. And although it's not obvious from a picture like this, the deepest clouds are in an annulus, like a donut, surrounding an often clear region called the eye. It is this annulus, which we call the eye wall, under which the strongest winds and the heaviest rains occur. And then outside the eye wall, the rain is arranged in these beautiful sort of spiral patterns that there's a suggestion the Mayans and Cubans understood a long, long time ago. When you look down from the top, you're seeing the top of the storm. It's at an altitude of 15 kilometers or so above the surface. And the temperature up there is some of the coldest temperatures you can find anywhere in the atmosphere, actually. It's minus 70 degrees C or so up there. And that actually turns out to be important to the physics of the storm. So what you see when you look down from space are ice clouds. These are all composed of ice crystals. The eye wall clouds extend down close to the surface of the ocean. Now, we've been flying research aircraft into hurricanes since 1943. It's now routine to do this in the Atlantic. And when you fly into these storms, this is a picture of what the eye wall looks like, or the view of the eye from the center. It's actually very difficult to do justice to this view with any kind of two-dimensional photo. One of these days they'll take an IMAX camera or something into a hurricane. Hasn't happened yet. But it's a magnificent view. It's like standing in a stadium. You've all stood in stadiums, but the stadium is 20 miles across and 10 miles high. And it's beautifully white, the blue of the stratosphere up here. There's often kind of a cascade or waterfall of ice crystals falling down the inside of the eye. The base of the eye near the sea surface is filled with low clouds, but is otherwise clear. It's a fabulous view. I think everyone should see this. So when I retire, I'm planning to start a hurricane safari operation, paying customers. If you'd like to sign up, you can come and see me. People ask me all the time, is this a rough ride? Not really. Not most of the time. I can truthfully say, having been on quite a few of these, that I've had much worse time on United Airlines. And I'm not joking. Now, let's talk a little bit about the climatology. This is a nice map. I think I shamelessly lifted that out of the Wikipedia, showing the tracks of tropical cyclones over the world from 1945 to 2006. And the colors are an indication of how strong the winds are in the storm. These are tracks that typically in the northern hemisphere start out, move off to the west, and curve up to the north and east. There are 90 such storms, more or less, with a standard deviation of 9, every year around the world, of which only 11% occur in the North Atlantic, although the North Atlantic storms get far more press than the other ones. So if you look at this map, these are the storms most of you are familiar with that start off the coast of Africa, anywhere from there to the Gulf of Mexico, move west, curve off to the north. People are less familiar with the eastern Pacific storms. There are lots of these, but very seldom do they influence land. Every once in a while, one will make it out to Hawaii. These are the storms that nailed Kubla Khan. These are the western Pacific storms. 40% of the world's tropical cyclones occur there, all the way across the South China Sea. And then the northern Indian Ocean is quite active, particularly the Bay of Bengal. And in the southern hemisphere, there's another belt going across the South Pacific and South Indian Oceans. There's a storm called Sandra that's just swung down between Australia and Vanuatu. You'll notice that there are no storms near the equator. Physically, you can't have rotating vortices near the equator because the Earth's axis is more or less perpendicular to what you're calling up, and you can't have a long-lived rotating storm in that. So if you're planning to sail around the world and you don't like hurricanes, if you stick to the equator, you'll be fine, although you might have other problems.
There are far fewer in the southern hemisphere.
There are fewer, that's right. There's the southern hemisphere is only about 38% of the total. They're more in the northern hemisphere than the southern, which is an interesting point. Why should there be that asymmetry? We can come back and talk about that if you like. Yeah. A little bit about the physics. I actually think the physics are really interesting. For atmospheric phenomena, they're relatively straightforward, not in an absolute sense. And the reason that we can talk about them a little bit more easily than we can, say, the kinds of winter storms, which we had a lot of this winter, for example, in New York, is that they're approximately circularly symmetric, or at least it seems that you can capture most of the physics by approximating them as being circularly symmetric. And at least for some of their lifetime, they're also approximately steady in time, or they can be. So you can describe them as you can idealize them as a two-dimensional phenomenon. And that makes them a little bit easier to talk about. So here's a map that's supposed to be a vertical slice through a steady hurricane, circularly symmetric. So the axis of the storm is over here on the left. This is going up 16 kilometers, about 10 miles, and then out from the center to 200 kilometers or so. And as Olivier mentioned in his introduction, the energy cycle of a hurricane, which is probably the easiest thing to understand about it, is remarkably similar to an ideal Carnot heat engine cycle. We say a little bit about that. Carnot was a French scientist who is usually credited with founding the science of thermodynamics, largely to explain why steam engines worked. The Scots kind of perfected the steam engine, but they didn't really have a theory for steam engines. The French wanted a theory, and Carnot made some very fundamental discoveries. And the Carnot engine is a variety of heat engine, which is just a device that takes one form of energy, heat, and turns it into another form of energy, in the case of the hurricane, wind. Carnot made some very important fundamental discoveries about how these engines work. One of them was you could never take all the heat energy and convert it into other forms of energy. You could only take a fraction, and that fraction depends on the difference in temperature between the place where you put the heat into the engine and where you take it out again. And the other thing that Carnot did was to show that for any engine operating between two fixed temperatures, there was a particular thermodynamic path that maximized the conversion of heat into other energy. And that path is called the Carnot cycle, okay, after Sadie Carnot. Now, if you look at a thermodynamics text, all of them will tell you about the Carnot cycle, and none of them, to my knowledge, actually give an example of one because it's too perfect. It doesn't really occur in the natural world, or so we thought. But it turns out that the hurricane's remarkably close to an ideal Carnot cycle. It's almost spooky in a way. So let's see how that works. If you were so unwise as to take a hot air balloon ride in a hurricane and start here at A, what you'd find is that you drift in toward the center, of course, while rotating rapidly around the storm. And when you got to the eye wall, this is the band of very heavy cloud, the strongest winds there, you go shooting up the eye wall and out. And then over a period of many weeks, actually, you slowly come back down in service. I don't advise you to try this, but if you just do it as a thought experiment. Now, the lurid colors on this diagram are a measure of the heat content, for those of you who've had some thermodynamics, literally the entropy of the system. And that entropy can only be changed by an external source or sink of heat. All right? So let's follow the air as it spirals in from A to B. You see it's going from low entropy blue to high entropy red. And that's reflecting the fact that heat is being added to the air. And the boiler room of the hurricane is the air flowing in along the surface. It's acquiring heat from the ocean. That's what drives the hurricane without any doubt, is the acquisition of heat from the ocean. That's why they always start to die when they go on land, because there's basically no heat content in the land. Now, the transfer mechanism is mostly evaporation of water. For the same reason you feel cold when water evaporates from your wet body, even on a hot day. That's because heat's being drawn out of your body. It doesn't disappear, it gets added to the air. Well, the same thing's happening in a hurricane. Heat's being drawn out of the ocean, but the ocean is such an enormous heat reservoir that it doesn't really change the temperature that much. And it increases the entropy of the air. Then, as the air goes up this leg, it conserves its entropy. You can call that an adiabatic expansion. It's going up a line of constant color on this diagram. And then the heat that it got from the sea is radiated to space in the form of infrared radiation, high up in the atmosphere. The entropy returns to its normal value, and then you have another leg in which the entropy is conserved. And that turns out to be the four legs of an ideal Carnot cycle: isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression. It's the most efficient engine that nature could contrive to turn the energy that results from evaporation of seawater into wind. Okay? It's a very, very efficient engine. And it operates on a big temperature difference. The absolute temperature of the tropical ocean is around 300 kelvins. And the absolute temperature of the air flowing out of the top of the storm is closer to 200 Kelvin. That gives you an efficiency of about a third, which is pretty good for a natural heat engine. Okay. Now, that's just saying what I just said about the Carnot cycle. Now, I'm not going to go into this, and don't worry, I'm not going to flood you with equations, but I wanted to show you that there exists one that comes from the Carnot cycle that is sort of the E equals mc squared of the hurricane world. It's essentially equating the generation of mechanical energy by the Carnot cycle with the dissipation of energy by friction. And when you do that, you get an expression for the wind speed squared. We call that the potential intensity, V potential squared. And over on the right-hand side are a bunch of things that include the difference between the temperature of the sea surface and the temperature at which you take air out of the heat out of the system. And then the driver is this sort of evaporative potential, this term far over on the right. Let me see if this laser might work better than the other one. Is that better? I don't know. Anyway, it's this. Nope. Much better. Okay. Yeah, I could try that, but sometimes that results in the slides advancing unexpectedly. In any case, that allows us to calculate sort of an upper bound on the intensity of the hurricane, which we call potential intensity. And here is what that looks like if you graph it as a function of how cold in degrees C, in this case, the outflow is, and how warm the sea surface is. Typically in the tropics, we're somewhere here in this diagram around E, and this is contouring the peak wind speed you can theoretically have in a hurricane as a function of these two things. Around 80 meters per second, which is close to the largest velocities we observe in the strongest hurricanes. The equation actually has a singularity in it, which is very interesting. If you go to very high temperature or very cold upper atmosphere, call that the hypercane regime. That's a story for another day. We don't live anywhere near it, but it's an interesting phenomenon. If we map out the peak potential intensity climatologically we have in today's climate over the course of a year, this is the peak that you have any time of the year, you'll see a map like this, and it sort of shows that the potential intensity is high throughout most of the tropics. And if you remember that diagram I showed you of hurricane climatology, this indeed captures the main hurricane belts. But the Carnot theory doesn't know that hurricanes are mechanically impossible on the equator, of course. In practice, we don't ever see hurricanes form where the potential intensity is much less than about 40 meters per second. It's just an empirical observation. Okay, now what about climate change? Well, we have a bit of a leg up now, theoretically, because we have this bound. And at least we can ask, how does this bound change when you change the climate state? It's not fixed bound. If you change the ocean temperature or other aspects of the atmosphere, you can change that bound. But we also have observations of hurricanes going back a while. And we can see to what extent we can learn about climate change directly from the observations, but also from the theory. So I'm going to show you a metric called power dissipation. Rather than counting hurricanes and talking about their numbers or talking about Saffir-Simpson categories, I prefer to use this metric. What it is it's the integral over the lifetime of the maximum wind speed cubed. Okay, now why should we come up with a metric like that? It turns out you can show that that quantity is proportional to the total power dissipated by hurricanes over their lifetime. Also the total conversion of ocean evaporation energy, if you want to think of it that way, into mechanical energy. And so it's an energy metric. And if you have very high power dissipation, you almost, by definition, have a very destructive hurricane. So it's also kind of a measure of destruction. In fact, some people mistakenly call this the potential destruction index, but that's not really what it means. Okay, now let's look at how this has behaved in the Atlantic. I'm going to concentrate on the Atlantic now, not so much because we live there here, but because far and away the best hurricane data for a lot of different reasons in the Atlantic. We've been measuring hurricanes systematically the longest in the Atlantic. It's the only place that we have continuously flown airplanes into hurricanes since 1943. Elsewhere in the world, our estimates of hurricane intensity are very rocky even today, even with satellites. That's another story. So this is power dissipation by Atlantic hurricanes going back to 1970. Before 1970, the hurricane data starts to get flaky. That's another interesting story. And the units wouldn't be very familiar to you anyway, but if you just look at the numbers in the axis, you'll see that from the 1980s to the first decade of this century, hurricane power has gone up by 50% or more in the Atlantic. These are big changes and big swings on sort of an 11-year time scale as well. So what's going on there? This is the same graph, but I've overlaid in blue a completely independent quantity. It's simply the ocean temperature in the tropical Atlantic where hurricanes typically develop during hurricane season. That's the blue curve. You can see some correlation there. In fact, the correlation is very high between those two quantities. The Carnot theory predicts there should be a correlation. It doesn't predict it would be that high. And it certainly doesn't predict that a mere half a degree centigrade rise in ocean temperature would double hurricane power. So we have some interesting problems to work on there. There's a much greater sensitivity of Atlantic hurricane power to ocean temperature than we would have thought was possible based on what little theory we have. Now, as I mentioned before, we don't have very good records of hurricanes going back. Although there are hurricanes in the database that go all the way back to the middle of the 19th century. On the other hand, we have very good records of ocean temperature going way back. And this simply shows, again, the temperature of the North Atlantic Ocean, but I've converted it into the units of power dissipation. So what I've done in this case, if I go back, is I've taken the relationship between hurricane power and ocean temperature from this graph during the modern era where both of these measurements are fairly robust and use it to make a backward projection of hurricane power. This is a dangerous thing to do because just because you've observed a relationship between two quantities for the last 40 years doesn't mean that that same relationship obtained before that. But okay, let's just try it, all right, and see what happens. And you get this sort of backward projection of hurricane power, which shows that it sort of went up into the 1930s and then dropped into the early part of the century. All right, what do you make of that? Now we're going to do something really brave. We're going to take the hurricane power from the actual hurricane data set as flaky as it is and overlay it on the same map. That's the red. All right. Not bad. All right. In spite of all the problems and things that we have about the hurricane data, the fit isn't bad, except...
What's the 10-year oscillation that you see?
That's a very good question, and wouldn't we love to know the answer to that? Mm-hmm. It's actually 11 years. Now, what is that? All right, so, of course, we thought it was a solar cycle. This turns out to be a peak at 11 years. So we got very excited because it is known that the solar cycle has an influence on the atmosphere, not very much. And I put a student onto that, and he came back and said, I'm very sorry, Professor, but it's not coherent. It doesn't actually match up with the solar cycle. We've done a lot of work on that. It would have been very lovely if we could say that, but we're left not knowing what this 11-year cycle is. I think it's a very interesting problem. It's a very strong spectral peak. And if it were coherent with the solar cycle, we'd have a lot to talk about here, but no dice. There's this period from 1939 to 1945 where the hurricane power is much lower than the fit to SST would predict. That range of years may mean something to some of you. The fact is that in that period of time, we relied heavily on ships for reports of hurricanes. During World War II, ships were not permitted to radio information normally. And perhaps more importantly, they traveled in convoys, which was a tactic to avoid submarines, and it was great for that, but a lousy sampling strategy for the weather in the North Atlantic. So we think that's a World War II anomaly, but we're not sure. Okay, so if there's a spectacular relationship between hurricane power and temperature, we could ask a second question: why did the temperature do what it did over that time? Forgetting for the moment about the 11-year cycle, which is very interesting, but this sort of longer-term seesaw and trend in temperature, what was causing that? Well, let's have a look at it again. So what I'm showing you here in blue is the temperature of the tropical Atlantic during hurricane season, going all the way back to the middle of the 19th century, except that I've passed it through a filter which basically smooths it over 10-year periods. It's a 10-year running average. It's not very sophisticated, to bring out the longer-term variations. And you have this very interesting seesaw. It goes up, it goes down, it goes up. And I've subtracted from that the long-term mean, so it's centered at 0 degrees C. This is anomalies from the long-term mean. The green is exactly the same exercise, but performed on the entire northern hemispheric surface temperature in the months of August through October. Okay, so it's the whole northern hemisphere, land included. And it just illustrates a simple point that's important, that is on these long time scales, the tropical summertime North Atlantic temperature isn't doing anything different from the hemisphere as a whole. All right? And that makes our life a little bit easier because we can ask a maybe somewhat easier question: why did the northern hemisphere temperature do that? Do this sort of seesaw number with a trend over the 20th century? Well, the reason that's somewhat easier is that there are armies of climate scientists working on that problem, right, as opposed to working on the temperature of the North Atlantic. And it's interesting to see what conclusions they've come to. And one of the tools to do that is climate models, for all their flaws and difficulties. When you run them over the 20th century with all the different things that were changing over the 20th century, which is sunlight, volcanoes, greenhouse gases, and other aerosols, this is what happens. This is the globe. Now we're backing off to the whole globe, not just the northern hemisphere. This is the observed global mean temperature going back to about 1900. It sort of went up in the early part of the 20th century, leveled off, and then started to go up more rapidly. The gray and brown curves are running a suite of climate models over that period, which kind of does the same thing. Now, to be fair, those models were tweaked more or less, although a lot of the modelers don't like it when people say that. I'm fairly convinced that they were tweaked to get a nice match. But with the models, at least we can ask what caused the models to temperature to change. And we have a very well-defined answer to that question. So these are the main components that go into this brown curve. And there are 4 of them. 2 of them are completely natural, changing sunlight, that's the red curve here, and volcanoes, which cool the planet by putting aerosols in the atmosphere that reflect sunlight. That's the green curve. Then there are 2 man-made components, the greenhouse gases, methane, carbon dioxide, and so forth. And then there's a negative effect, which is air pollution, aerosols that reflect sunlight, mostly sulfate aerosols. So it's a cooling effect. And when you add up all these color curves, by definition, you get the Brown curve. And so what you can see right away is that at least up until the mid-1970s or so, the answer to that question is not a simple answer you can put on your bumper sticker of your car. A lot of different things contributed to the change in the early 20th century. Slightly increasing sunlight, a statistical absence of big volcanic eruptions from 1918 to 1960, just a fluke. There weren't any big volcanic eruptions. The atmosphere got clean during that period. Some contributions from greenhouse gases and also from sulfate pollution. But in the last 30 years, this big uptick that you see toward the end of the century is dominated by greenhouse gases. So when we go back and we look at that seesaw from before, explaining that is not easy. One thing we can say for sure is it is not an oscillation. Now, you know, a good statistician will look at a record like that and say, show me 20 ups and downs, and then I'll talk about cycles. But a meteorologist only has to see 2 peaks in one trough or the other way around to call it a cycle. And unfortunately, this gets called a cycle. But there's nothing, we don't think there's anything cyclic about it at all. It's just the way the different radiative forcings have added up over this period. So this big increase, 20th century, a little bit of solar, absence of volcanoes, and greenhouse gases. This downtick driven mostly by man-made pollution, aerosols, and things like that. Then we had the Clean Air Act in the United States, which really cleaned up the sulfates over the North Atlantic. That and the greenhouse gases have led to this big uptick. So it's not a simple picture, but it is understandable, okay? But we don't think there's anything oscillatory. So people talk about multi-decadal cycles of Atlantic hurricane activity. I don't think there's any evidence for that at all, actually. Okay. Now, that's the globe. What about the northern hemisphere, to come back a step? Well, of these 4 forcing agents, the sulfates are a bit special because they only stay in the atmosphere about 2 weeks. And for that reason, they're concentrated near their sources, whereas the other agents are pretty much spread over the world. Now, it turns out most of the pollution, as you might guess, is in the northern hemisphere. Most of the sulfate aerosols are in the northern hemisphere. So Mike Mann and I, a few years ago, said, well, okay, let's do this. Let's look at the global surface temperature. That's the red curve again, going back to 1870. Let's look at the northern hemisphere temperature. Actually, this blue curve is the tropical Atlantic Ocean temperature, which is similar to the northern hemisphere temperature. Now, this light blue curve that starts at 0 and goes down is a record of sulfate emissions, okay? And we asked a very simple question: can you add the sulfate curve to the global temperature and get back the North Atlantic temperature? And that's what this red curve is. It's pretty good, all right? So the hypothesis is that the reason that the northern hemisphere cooled and the tropical Atlantic so much in that period was of man-made air pollution. All right? So I'm fairly convinced at this point that the big hurricane drought that we had in this country from the 60s through the 80s and early 90s was actually a man-made hurricane drought more than anything else. So that was the black lining on the silver cloud of the Clean Air Act is it cleaned up the aerosols and let the North Atlantic warm up again, especially aided now by greenhouse gas increases. Okay. Now let me mention a little bit about the feedback of this to the global climate system. Whatever is causing hurricanes to change, they are changing, okay? And does this change have any effect back on the climate system? Well, we think it does. But the route that it causes, that takes the change is actually very interesting. And we're not very sure of this. This is fairly recent research. One thing we know for sure is that hurricanes do a spectacular number on the upper ocean. And this is showing, sorry. Can everybody hear me now? I'll try not to do that again. This is showing the difference between the surface temperature of the water of the Gulf of Mexico before and after 2 hurricanes passed. This is Hurricane Emily and Hurricane Dennis, and they passed along these black lines. And you can see to the right of the path the spectacular cooling of the upper ocean. Now, this has been known for decades, And it's also understood why there's a cooling. You might be tempted to think, well, of course you're evaporating, well, the seawater is going to get cold. True, but these wakes are depressed by several degrees centigrade, and the evaporation can only explain a few tenths of a degree. Most of the cooling is because you're violently, through turbulence, violently mixing the warm waters at the surface of the ocean with colder water that is invariably found deeper down in the ocean. This mixing is very interesting and has some very interesting consequences for the climate. Here is a record of the temperature of the water as a hurricane goes over. You see it drops, in this case, about half a degree, and then over a period of tens of days recovers. Why does it recover? It recovers because the cold water basically gets reheated by the sun. Now, that sounds like a trivial statement, but it turns out if you add up all the heat added to the ocean, and this is real heat in the sense of vertically integrated heating of the ocean, from all the wakes that hurricanes all over the world produce, it's not a tiny number, it's a pretty big number. How do we measure that? Well, it turns out that, I'll come back to that chart, various different estimates of this heating are shown here. This is the estimate I made some years ago with huge error bars. It was around 1 petawatt, that's 10 to the 15th watts globally, of ocean heating attributable to this wake recovery. A later estimate by Stryver and Humer put it down at about a quarter of that value, and then there have been some other estimates. So somewhere in this range, but this number up here is the total amount of heat transported by the entire ocean moving poleward toward the poles. So whether you're down here or up here, it's still not a trivial fraction of that. And it turns out that violently mixing the upper tropical oceans causes enormous lateral heat transports to occur. And that's one way the oceans, that hurricanes can indirectly affect climate, we think. Now, as you can see from this chart, we're far from having a good grasp on these numbers, but it's kind of an intriguing possibility. One of the things that this might do is be one of the mechanisms by which El Nino events are triggered. El Nino is a phenomenon of the tropical Pacific. Roughly, it's not periodic, roughly every 4 years, the waters of the equatorial eastern Pacific warm up dramatically and affects weather all over the world, but particularly in the tropics. Now, in the theory of El Nino, we're all sure about one thing, it involves both the ocean and the atmosphere, the interaction between these two fluids in fairly complex ways. But hurricanes may actually play a role in that interaction. I don't have time to go into the details here, but what I'm showing you here are two time series. The green is something called an ENSO, or Southern Oscillation Index. It's just an index of El Nino going back to 1950. And the blue is an estimate of power dissipation by near equatorial hurricanes in the Pacific, but lagged 2 years. In other words, that blue curve has been shifted to the right by 2 years. And there's a pretty high correlation between the two. It suggests when you have a lot of hurricane activity in the near equatorial Pacific, 2 years later you tend to get El Nino events. Other people looked at this and found similar signals, so it might be that hurricanes also play a role in some of these more local climate oscillations. That's all very recent, somewhat speculative research. These are not hard facts yet, but it's an intriguing suggestion. Obviously fascinating that there might be a connection between those two phenomena. We think, some of us, that hurricanes may help us explain some climate puzzles. This is the ocean temperature average east-west around the world in today's climate, going from the South Pole to the North Pole. So this terrific temperature gradient and a flat peak in the tropics, and then you go down to the North Pole. The two dashed lines show some estimates of what the ocean temperature might have been like 50 million years ago during a period called the Eocene, when the planet was much warmer. There was no ice anywhere on the planet, no ice in Antarctica or Greenland. And it's very hard to get climate models, not impossible, but hard to get them to produce such a weak temperature gradient. And you can make, if you dump a lot of CO2 in the atmosphere, you can make the poles warm, but then the equatorial regions tend to be much too warm. So one idea is that because it was warm, there might have been much more violent hurricanes over the oceans, whose indirect consequence was to cause a big flow of heat in the ocean toward the poles, which might help explain that. Again, at this stage, fairly speculative, but another possible role for hurricanes in the climate system. Okay, let me finish now, the next 10 minutes or so, to ask the question, what are we in store for now as we warm the planet? And the first part of this will be trying to get a handle on the more general question of how do we use physics and not just statistics to estimate hurricane risk. This is very important. So forget about climate change for a moment. Let's talk about hurricane risk in New York. You all just got battered very badly in the fall by Sandy, right? Wouldn't you like to know, if you were a citizen or a planner, were we looking at a once-in-a-1,000-year event, or were we looking at a once-in-a-100-year event? It'd make a big difference. If it were a once-in-a-1,000-year event, probably not worth spending a lot of money building seawalls and things, if that's not likely to be repeated, but it's going to happen in 5 decades or a century, maybe it'd be worth it to try to do something about that. The problem is hurricane records go back only about 100 years, and probably not very good records for more than about 50 years. So just using historical storms isn't necessarily going to provide a very good estimate of that. And all the risk models that are out there, some of which are very expensive to buy, by the way, have been come up with by mostly statisticians, all right, looking at historical records. That's fine. That's a good start. But we ask the question, can we use another way of knowing the world, physics, to help estimate hurricane risk? And I'm going to tell you a little bit about that, and then use that method to help assess risk in the present climate and also going forward. Okay, so at MIT, we've come up with this sort of method for doing that, and it begins with either a climate model or something called a reanalysis data set, a gross, coarse rendition of the climate, including its time variability. The problem with climate models and these reanalysis data sets is they're too coarse to resolve hurricanes. They do get something, they get facsimiles of hurricanes, but they're not very strong, and they don't tend to have all that great climatology, so it's very dicey to try to use those to estimate risk. So what do we do about that? So the method we came up with is a kind of downscaling, and what downscaling is to say, well, you start with this coarse climate. Now let's embed within that climate a much finer computational model that does resolve, in this case, hurricanes, and run that within the coarser model. That's called downscaling. The way we do that is a little interesting. We begin with the coarse grained climate state, and then we seed it. And the way to think about that is, give me the climate, I'll go out and buy a package of, go to the garden shop and buy a package of hurricane seeds, okay, and just toss them into the climate state. And think of it that way, all right? So you begin with these seeds. Then the next question you ask is, where did they go? That's an easy thing to do, relatively, because hurricanes, pretty much like corks in a stream, just move with the large-scale flow in which they're embedded. And we know what that large-scale flow is from the climate model. So we move those seeds along, but the critical step is to ask, how does the wind field associated with these proto-hurricanes evolve? And for that, we use a coupled ocean-atmosphere hurricane model that was originally developed to help forecast real hurricanes in real time. It's a very, very fast model, so we can afford to do this over many tens of thousands of such seeds. When we do that, we find that something like 98% of the seeds we put down just die, okay? Which is unfortunately about my success rate as an amateur gardener, okay? It's about the same number, 2% survival rate. And they die because they've been put down in a bad environment, all all right? They're not too much wind shear, the water's too cold, something like that. So we regard the survivors as constituting the climatology of hurricanes. Does it work? Well, we have to run lots and lots of statistics of the surviving storms against historical data. I can't show you all of that. If you're interested, I can direct you to papers, but here's sort of a eyeball test. This is a set of 1,000 tracks produced by downscaling something called a reanalysis data set, ERA 40, over the world. Again, the colors denote wind intensity. And pretty much you see hurricanes, these hurricanes are where you expect them to be. There's the Atlantic belt. There's even one in the South Atlantic. Historically, there's been a few in the South Atlantic, not very many, and so forth. So, but if you run more rigorous statistics, you see things like this. This is the number of storms. This happens to be for an Atlantic data set in red, whose lifetime maximum wind speed exceeds the value over here on the left axis. So as you go to higher wind speeds, there are fewer and fewer storms. And the blue is from a somewhat more limited historical data set of actual hurricanes. So you have to do lots and lots of comparisons like this to persuade yourself that, yeah, this sort of random seeding and natural selection works pretty well, and the hurricane model is able to capture the full intensity of storms. Okay, so we now have a way to do that. Just to continue with this, this is an example of one of these synthetic hurricanes that happened to influence New York City. This one developed on the 4th of September and traveled up the East Coast, just inland of New York over New Jersey. And the red colors show the peak wind speeds in the storm. Here is something called a wind swath associated with that event. So the storm moved up along this black line, and the contours enclose the peak wind experience at every point during the event. Okay. So the strongest winds are to the right of the track of the storm. This one really got New York City with about, hurricane force winds in this case. But we can easily create data sets of tens of thousands of these storms and get some feeling of how they're related to climate. This is a little bit new, but we're also able to predict rainfall. So this is storm total rainfall for this event. So strong influence of mountains. So you get lots of rain over the White Mountains of New Hampshire, for example, and generally along the track of the storm. We couple these events to hydrodynamic surge models. So this is several of these that we've run. This is the mesh of two models. This gray one is a publicly available model called SLOSH. It's a surge model. And then the blue and red dots are the grid nodes of an unstructured grid of a much more sophisticated surge model called ADSURT. And we drive those models with the wind fields produced by our synthetic hurricanes. And so, for example, this is a hindcast of the storm surge peak magnitude during Hurricane Irene with the surge model. Okay, so you get peak surges of about 1 1/3 meter up here, northern New Jersey and so forth. And this is a hindcast of Hurricane Sandy, whose track came in along here. It predicted a surge of 3 1/4 meters, which is about right. I'll show you that. This is a similar surge forecast, but with a much more sophisticated wind model, which is actually designed to forecast real hurricanes in real times. Now, about a year ago, a colleague of mine named Lynn and I published a paper showing estimated surge risk at the Battery in New York. This was last February, 2012, so it was pre-Sandy, showing that a 3-meter surge in the present climate, according to this downscaling, could be expected every 500 years or so. Okay, now that turned out to be about Sandy's surge when you subtract the astronomical tide away from it. It's about 3 meters. And so let's use this method now finally to look ahead, because we can do the same thing with climate models. We don't have to rely on climate data sets. And we're going to look at what happens when you apply this to 5 different climate models which you see here. Some of you who know those models, otherwise they're just different climate models run by different centers around the world. And we're going to compare two periods, an historical period, 1950 to 2005, and then the period 2006 to 2100 under the next IPCC report's emissions scenario, where carbon dioxide keeps going up until the radiative forcing is 8.5 watts per meter squared. So it's a pretty hefty increase. Unfortunately, that's about the path we're on right now. And this is new. I don't think anyone's seen this before, except maybe one or two talks. This is the global frequency of hurricanes downscaled from these 6 models, 5 or 6 models, showing the median prediction in red and then the 25th and 75th percentiles among the models by these boxes. And you can see it actually shows a fairly big increase in the number of storms going forward, which is a little bit different from projections using other methods. And if you look at where the changes occur, this is changes in track density, mostly in the northwestern Pacific and the South Indian Ocean, also in the Atlantic. And only in the South Pacific, where there aren't very many storms today, do you see a decrease. And this is a little bit more meaningful. It's power dissipation by tropical cyclones. That's also more or less forecast to go up, although there's a lot of disparity among the different global climate models. And the power dissipation changes are also mostly in the Pacific and South Indian Oceans, but a little bit of increase in the Atlantic as well. Okay, I think I'll skip over that, go to a summary. The main point I want to make here is that main points begin with the observation that hurricanes have had a very substantial effect on civilizations going way back and on the course of history. There's not much doubt about that. They're almost pure examples of Carnot heat engines that give us a little bit of a leg up in trying to understand how they work and how they might respond to climate. They may have, this is still work in progress, they may have substantial feedbacks on the climate system. So we shouldn't necessarily just think of them as responding to climate. They might actually be players in climate. We can use very simple models to downscale hurricanes from global climate simulations, which are not themselves capable directly of simulating them. And studies based on this downscaling suggest that there is some not trivial sensitivity of hurricanes to the climate state, with the suggestion of an increasing incidence of particularly intense storms as the climate warms. And I'll leave you with that. Thank you for being so attentive.